LeChatelier's Principal Lab Part 2. Just to review, conditions for equilibrium. We have an equilibrium system here, and it's a balance between reactants and products. Rate of forward reaction equals rate of reverse reaction. It's a closed system where nothing is added or removed. We got H2O liquid going to H2O gas, H2O gas going to H2O liquid. I guess it's a little bit hard to see this flask right here, but that is what's going on at equal rates. We'll throw that in there right there. Okay, another equilibrium system is we have Fe plus 3, and that is, it's a little bit hard to see, but that's right here. It's kind of that orangish red. It's staying the same color, and the reason it's staying the same color is because it's in equilibrium. Fe plus 3 and SCN minus are combining to form FeSCN plus 2, making it more red, but the FeSCN plus 2 is splitting up, making it form Fe plus 3 and SCN minus, which makes it less red. So the forward and reverse reaction are going at the same rate, which makes the color stay constant. Part of it's making it turn more red, part of it's making it turn less red, so it's staying the same or the way it is. All right, LeChatelier's principle we looked at. I think I'm going to get this out of here. And we said, if a stress is applied to a system in equilibrium, the system will change to relieve that stress. Or if a system in equilibrium is subjected to a change, processes occur to counteract that change. In other words, if a system in equilibrium is subjected to change, shift happens. It'll be your job to know your shift. So for this last reaction we did with the iron and SCN and FeSCN plus 3, we looked at this equilibrium system and we looked at concentration changes. We found out that if we increased Fe plus 3, adding more of something makes you want to get rid of part of that. It shifted the equilibrium right, making it turn more red. Same thing when we added SCN minus. If we removed Fe plus 3 or SCN minus, then it shifted toward making more of that. Today we're going to look at a system as far as temperature, because it says for both concentration and temperature changes, shift away from what you add, shift toward what you take away. So we are going to look at this equilibrium system where we have COCl2, and I have some right here, and it's really hard to see the color, but it's kind of a pinkish color right here. And what I'm going to do is I'm going to put it to the side for now, but that is an equilibrium system with COCl4, another ligand that has more of a bluish tint, and then there's H2O, and it forms this COH2O6 ligand, which has more of a reddish pink color, probably more pink, and then 4Cl minus, which is clear, and then there's heat on this side. So we're going to learn that because this is an exothermic action, or heat is on the right side. Heat is just like anything else, and we're going to find out when we put it in a hot bath what happens and try to predict what's going on there. So let's take this substance and let's get a couple baths right here. Here's a hot bath over here. Here's an ice bath right here. And I don't know if we can prop those up a little bit more. I think we can. Let's try to do this. And we'll get rid of these. And here we go. We got our hot bath here, and we got our ice bath here. And I'm going to take this substance, and hopefully you can see that here. It looks kind of pink. I'm going to put it in the hot bath, and let's see what happens to it. I feel like I'm creating all kinds of nasty shadows here, but let's see what happens as, it looks like twilight, changing to nightfall. And it looks like it's turning a dark blue. All right, and that's pretty hot water right here. I'm going to take this and do the opposite thing. I'm going to take the same thing, put it in the ice bath. Here, I better show this here. Okay, you think I'm probably putting something else in there. I'm not. Trust me, I'm sure you do. Yeah, right. And I put it in the ice bath and we'll see what happens to it. All right, and then we're going to kind of figure out this thing about the equilibrium shifts. So when I put it in the hot bath, it turned really a dark blue. I'm putting it in the ice bath. Oh, daybreak. Looks like it's getting a little lighter. And takes a little bit of time for those molecules. Again, there's collisions between the hot molecules and cold molecules, and eventually enough of them bump and you get that temperature to start changing in there and start getting that color change right in there. Okay, let's go back. I think we've got this cooled down pretty well, and it definitely looks a lot more pink than it was before. All right, I'm going to move the hot bath and the cold bath for a second. I'll put it back in the hot bath, so we'll just take a look at it there, and let's go to this reaction right here. So, I'm just looking at it, and what happens is I think I'm going to go to this chart right here, okay? And it looks like I need to tweak this, adjust my screen a little bit. Let's see, I think you can see that. And think about heat as any other reactant. I add heat, so I increase that. And what's going to happen is the system is going to shift away from that heat, trying to dissipate some of that heat. So that will pull some of the heat away by shifting left. Everything on the left-hand side, or I'm sorry, everything on the right-hand side is going to decrease. So I added heat, some of it goes away, this goes away, this goes away. The equilibrium shifts over to the left, because this is the middle of the equation, and then everything over on the left side increases. So if I add something to the right side, everything on the left, or if I add something to the right side, everything on the right decreases, everything on the left increases. Notice what happened. The pink thing decreased and the blue thing increased. So when I put it in the hot bath, I added heat, the temperature, it turns blue because we created more of this. Some of this pink thing turned into some of the blue stuff. Okay, what if you remove heat? Well, it's just going to be just the opposite. So if I take away heat, everything's going to shift more toward it to try to create some to compensate for that. So what happens is the blue thing becomes less, this H2O becomes less, the equilibrium shifts right, and then these two things increase right here. Okay, and notice the blue gets less, the pink gets more, so therefore equilibrium shifts to the right and it turns pink. So with concentration changes or temperature changes, shift away from what you add, shift toward what you take away. If I add heat, it's going to shift to the opposite side. Everything on the heat side is going to go down. Everything on the opposite side is going to go up. If I take away heat, then everything is going to shift toward that side. Everything on the opposite side will decrease. Everything on the side of heat will increase. And that's shown out by what we have here. I put it back in the hot bath. It turned like this. And I just want to do one other experiment where I add a little bit of water to this and watch what happens. So I'm just going to add some pure water because this is sensitive to temperature, but it's also sensitive to moisture. So I'm going to squirt some water in here and watch what happens. It gets pink. And I look at this system and I can say, why would that get pink by adding water to it? I'm going to throw that right in there. And if I look, H2O is on this side. If I increase the H2O, it drives the equilibrium this way. Some of that H2O will react with this and then form this right here. So it's not only sensitive to temperature of the system, it's sensitive to water. So let's say you buy a mood ring, okay? Is that sensitive to temperature and water? No, it's sensitive to how you're feeling that day.